The biker featured here was very close to the camera before he was clearly visible. Due to their lack of visibility, bikers who do not use proper lighting systems when they ride put themselves and others in danger. Also, many bikes who do use proper lighting systems could end up in this situation as well due to a dead battery.
The piezoelectric energy harvester for bicycles provides a unique solution to both of these issues. First, our system utilizes a high visibility LED that can be seen from over 500 feet away. Second, by harvesting the vibration energy present in the bicycle and converting that energy into electrical energy, the piezoelectric energy harvester is capable of providing supplemental power that charges the light's batteries during use. Hi, we're Electrical and Computer Engineering Senior Design Group number 14, also known as Those Kids Over There. And this is our senior design project, the piezoelectric energy harvester for bicycles. My name is Caden Monte, and I was in charge of power control, power storage, and enclosure design.
My name is Matt Goodlett, and I was in charge of voltage regulation and PCB design.
And my name is Lane Brammer, and I was in charge of piezoelectric research data and light control.
Conventional energy harvesters rely on, effectively, regenerative braking, which is a great way to pull out a lot of power from the system, but comes with a downside. That is, they pull some of the input energy from the rider to power the electrical systems while they're riding down the road. This effectively introduces an extra amount of drag to the rider and makes it more difficult to ride up hills and in general. The advantage of our piezoelectric energy harvester is that it actually picks up vertical vibrations as opposed to horizontal vibrations and horizontal momentum, which allows us to power our systems without inflicting any extra drag on the rider, because vertical vibrations in a bike typically just go to waste. So that allows us to power all of the systems that we need on our bike without the need to inflict more drag on the rider than is necessary, and allows us to conserve energy on the road and make it so that the everyday person can use this without any extra impedance on their day-to-day routine. Now, a lot of you may be wondering what piezoelectrics are. Piezoelectrics are a class of material that respond to mechanical vibrations by generating an electric charge across the output terminals. That is to say, as we vibrate this pad, we will generate a dampened sinusoidal function across the output terminals that we can harvest then. By applying a rectifier and some voltage regulation blocks, we are able to take in this positive and negative swing that can be quite high, up to 100 to negative 100 volts, and regulate that and rectify that down to a safe voltage that can be then passed into our batteries.
The operation of our system can be broken down into 5 distinct stages. At the first stage, mechanical excitation is fed into our piezoelectric generator block. The piezoelectric generator is responsible for converting the AC signal present on the terminals of the piezoelectric pads into the rectified signal that we see on the output of the piezoelectric generator. This is then fed into a voltage regulator. The voltage regulator limits the voltage from the output of the generator, which is capable of spiking up to 100 volts, to the 4.5 volts that is necessary for the circuitry in the remainder of the system. The 4.5 volt signal from the voltage regulation circuit is fed into the power storage block. The power storage block is simply implemented as a set of batteries. At the output of the power storage block, we have a continuous 4.5 volt signal that is fed into the power control block. The power control block is responsible for multiple things. The first thing that the power control block is responsible for is turning the rest of the circuit on and off. The other thing that the power control block is responsible for is generating a pulse width modulated signal that is capable of dimming the output light. This was implemented to help us conserve power at the output of the power storage. To farther limit the power consumption of our circuits, the output of the power control block was fed into another power-saving light control block. This light control block blinks the light at the output at approximately 2 Hz. This saves us about 50% of our stored energy. At the output of the light control block is our visible light. This visible light is visible from over 500 feet away. As the project progressed from its initial stages, many of the technical challenges we experienced stemmed from the relatively high cost of piezoelectric devices compared to the relatively low amount of energy that they are capable of generating. These amounts are in the ranges of hundreds of dollars per milliwatt of power. One of the other technical challenges that arose from this was that the amount of power necessary for high visibility light generation is much higher than we were generating from the piezoelectric pads. One of the final technical challenges that we experienced was that our technical knowledge was fairly limited in some of the key areas that we required to progress our project. Some of these areas included case design, PCB design, and piezoelectric materials and devices.
Our first technical problem was actually solved in a non-technical way. In order to avoid the high cost buy-in versus low power problem of piezoelectric materials, we reached out to various companies as a student group working on an educational experience, and were able to get an educational discount, contingent on the fact that we would give them our research data when we completed it. That brings us to our second problem of the high cost buy-in versus low light visibility output of the lights. So we were able to circumvent this problem by redesigning our project to include a battery bank, where we originally simply just had a capacitor that would charge as you would ride. The inclusion of the battery bank allows us to kind of soften the blow of the high power consumption there. And we also implemented a significant amount of power saving circuitry that drops our power consumption from the original design by about 50%. And the third technical problem that we had of lack of experience is not so much something that we solved, but something that we broke down over time simply through research and by getting hands-on experience in the lab.
The device is designed to have a removable lid so that the internal circuitry and controls can be accessed by the user. The top layer of the system contains the power switch here and a light dimmer switch here, which controls the brightness of the light, as you can tell when it's adjusted from full brightness down to minimal brightness, which is essentially, you can barely just see it, but it's essentially off to the naked eye. On the back of the device here is the mounting system. In its current configuration, it can be used to mount the system on the handlebars of a bike. When rotated 90 degrees, the mounting bracket allows the device to be mounted on the seat post of a bike facing the rear. The device also includes a mode switch here, which allows the device to be switched into demo mode to show that when shaken, the piezoelectric pad will produce enough energy to charge a cap, which can then be discharged through an LED to produce light. As you can see here, when the device is firmly placed on the table, the mechanical vibrations produced by the impact create vibration in the cantilevered piezoelectric pad. The weights at the end of the pad allow for greater deflection, therefore increasing the power output of the pads. In order to fulfill our engineering requirements, we had to design the case to be watertight. We used clear acrylic and acrylic glue to seal the seams and make sure that they were watertight. We also used caulking around all screw holes just to make sure that those were watertight as well. To verify that the case was watertight, we used two separate tests. The first test consisted of exposing the case to an extreme amount of water over a small period of time. This verifies its waterproofness in the case of splashes, spills, or some sort of spray. The second test was designed to simulate heavy rain. The case was exposed to a drip for a long period of time to verify that small imperfections in the case would not allow water to seep through and damage the circuitry.
Our project timeline breaks very conveniently into three separate terms. The first term was an introductory term for our project. The three main things that we focused on was piezoelectric research data, converting from a capacitor-based model to a battery bank model, and also narrowing down the scope of the project. So when we started this project, we were not familiar at all in any way with the piezoelectric effect or how piezoelectric materials work. So the first couple weeks of the term were devoted simply to familiarizing ourselves with the materials, reading research data that was out there, and finding out a way that we can make this work the way that we want it to do. The second thing that we did during the term was convert our capacitor-based model that we thought we were going to use to a battery bank model, simply to soften the blow of the high power consumption of the lights themselves. And the third thing that we faced, which is something that almost every group faces, was narrowing our scope down. It's very easy when you start a project to get a very overbroad view of what you think your project can do, and it can quickly spiral out of control. And so our first term was devoted very heavily to making sure that our ideas were within the scope of the project and that they were attainable.
A large amount of time during the second term of development of the project were focused on developing the printed circuit board and the enclosure. These were both fairly difficult for us, as none of us had any experience with any sort of 3D modeling software or with PCB design tools. A second large portion of this term was devoted towards developing a lot of power-saving circuitry. This was necessary because of the relatively low power of piezoelectric devices versus the amount of power that we needed to generate highly visible light. Finally, the last portion of the term was devoted towards implementing a fully functional project prototype.
During the third term of the project, our team has been working closely with our project sponsor in order to start the patent process, in hopes that we can get a patent for our design. We've also been working to redesign the PCB to include additional features, including using multiple piezoelectric pads. We've also been researching additional ways to improve the project and advance it further in the future.
Now that we've reached the conclusion of the project, we're able to look back with some clarity and take away some lessons that we've learned during the process. First, using agile development as opposed to waterfall to make iterative design steps of the project made the project run smoothly throughout.
Another important aspect of completing the project on time was diligently avoiding scope creep. It's important to make sure that the project doesn't become too large or nebulous to understand.
And finally, you need to do a little thing each week. Projects like these are much too large to do in a single weekend, and so taking iterative steps throughout makes it so that the project deadlines can be completed on time. This has been a short introduction to our project. Thank you for your time.